Hello everyone, my name is Perla Pérez and I will present to you my poster titled Electrolyte Influence on Electrochemical Oxidation of CVD derived manganese 4 oxide to delta manganese dioxide. To start with an introduction, manganese oxide has attracted attention as a pseudocapacitive material used in supercapacitors. This interest comes from its natural abundance, its non-toxicity, and its ability to form multiple oxidation states that create various crystallographic phases. One notable phase is delta manganese dioxide, also known as Burnside, which has a layered structure with intercalated ions and water molecules. This layer structure can engage the specific capacitance in supercapacitors, making its synthesis highly important. The purpose of this work is to investigate the evolution of Burnside synthesis with different cations in the electrolyte through an electrochemical process using thin films of manganese 4 oxide, also known as Hausmannite, deposited by chemical vapor deposition. Now, how we did it? Well, we performed the electrochemical oxidation of the Hausmannite films previously deposited on stainless steel using the CVD technique. It consisted in applying a cyclic voltammetry for 3000 cycles at a scan rate of 100 millivolts per second in sodium sulfate, potassium sulfate, and lithium sulfate electrolytes, within a potential window of 0.8 volts. Samples were taken every 1000 cycles, and they were analyzed using SEM, Raman spectroscopy, and X-ray diffraction. Moving on to the results, the electrochemical oxidation with different electrolytes revealed distinct differences between the burn sites obtained. For instance, the CV shape with sodium sulfate electrolyte presents well-defined redox peaks around 060-045 volts. Here are the corresponding micrographs for every 1000 cycles. You can observe how, from a flat morphology, nanowalls appear at 1000 cycles and continue to grow with further cycling. Raman spectroscopy confirmed that these nanowalls have the characteristic spectrum of sodium Burnside, especially the bands around 400 inverse centimeters, indicating the intercalated ion in the structure. Furthermore, X-ray diffraction corroborates this Burnside phase at the end of the process, with the 001 plane being the most characteristic. In the case of potassium sulfate, the CV shape does not show intense redox peaks. However, the increase in current density with more cycles indicates the transformation of Hausmannite to Burnside. The micrograph also showed the appearance of nanowalls, but over time, these structures lose their verticality and become horizontal. Raman spectra for these samples reveal the characteristic bands of potassium Burnside, and X-ray diffraction at 3000 cycles confirmed the Burnside phase. Now, for lithium sulfate, the effect was different. The CV shape presents two pairs of redox peaks, one around 045 volts and the second around 073 volts. However, the increase in current density in the capacitive region is minimal compared to the other two electrolytes. This is reflected in the micrograph, where only a slight formation of nanowalls is observed, and by 3000 cycles no further nanowall formation occurs. Raman spectra at 1000 cycles show the characteristic bands of lithium Burnside, but these bands diminish by 2000 cycles and disappear by the end of the process. Consequently, X-ray diffraction does not show any peaks for Burnside. Lastly, in this image, I present the physical changes the film undergoes during electrochemical oxidation. The Hausmannite films start with a blue color, which changes to gold when sodium and potassium sulfates are used as electrolytes. With lithium sulfate, the final coloration is more purple. So, as conclusions, first, We discovered that the type of cation in the electrolyte significantly influences the shape of the cyclic voltammetry curves during electrooxidation. This indicates a strong cation effect. Second, we observe that the transformation from Hausmannite to Burnside is evidenced by specific redox peaks, shift in potential, and the increase in current density. Third, our micrograph showed that deformation of vertical nanowalls, which correspond to Burns outliers, was most pronounced when sodium sulfate was used as the electrolyte, compared to lithium sulfate, where the transformation was minimal. Additionally, our Raman spectroscopy results indicate that the vibrational modes of sodium Burnside and potassium Burnside increase in intensity and improve in profile with more cycles, leading to greater material density. However, with lithium sulfate, the Burnside tended to degrade as cycles increased. Lastly, X-ray diffraction analysis confirmed the presence of the Burnside phase when using sodium sulfate and potassium sulfate electrolytes, further supporting our findings. In summary, our research highlights the significant impact of electrolyte cations on the electrochemical behavior and structural transformation of manganese oxides. I would like to thank Tukanacit for all the financial support for this project and the International Materials Research Congress for the acceptance of this work. Thank you very much for your attention. If you have any question, don't hesitate to write to me at this email.